Okay, following on from my last video, which explained how to solve differential equations using the separation of variables method, I thought I would show you how to solve 4 particular questions which are modelling with differential equations. So question number 1, the rate of increase of a population, P, of bacteria is proportional to the size of the population. Initially, the population is 12,000, and after 24 hours, the population is 200,000. Find P in terms of T, where T is the number of hours after the initial population. Part B, according to the model, when does the population exceed 10 million? Give your answer to the nearest minute. And C, criticise this model. Okay, so first of all, whenever you have a modelling with ODE question, you tend to see this word here, rate. And a rate of change is a derivative. You need to make that link. That's what a derivative is. Now, usually, the rate of change in these questions is a derivative with respect to time. In this case, it is certainly that, because the population is going to change over time. So the rate of increase of a population, so that whole line there, mathematically can be expressed as dp by dt. Okay, P is the population, and this is the rate of change of the population over time. So we're told the rate of change of the population of a bacteria is proportional to the size of the population. And that is quite a common model for modelling population. Okay, so the rate of change of the population is proportional to the population size itself. Think back to your Key Stage 4 course in mathematics. We know that we can replace the proportionality symbol with an equal sign and a multiplicative constant. Okay, so that's what this line means. The rate of change of increase of population P of bacteria is proportional to the size of the population mathematically means dp by dt equals kp. And you need to extract that from the text. So now that you've got this, we can go ahead and solve this using the separation of variables. So I'm going to divide both sides by P, and I'm going to times both sides by dt. So I've got all the P's on one side of the equation, all the T's on the other side of the equation, and don't forget that K is just a constant, so it's not a variable. Now this doesn't make any mathematical sense at all, and I've treated this like a fraction, where it's really not. However, it behaves exactly like a fraction. All I need to do from here is put an integration symbol in here, and an integration symbol in here, and suddenly it makes sense and is a true statement. So from here, I just need to solve each integral. So the integral of p to the minus 1 with respect to p is the natural log of the mod of p. And the integral of k, it's just a constant, is just kt, because I'm integrating with respect to time. And now that both integral symbols have gone, I need to add my constant of integration. It's good to make p the subject. Okay, p varies as t varies, so p is the dependent variable and t is the independent variable. So I make p the subject by raising both sides as a power of e. So I can write that as e to the c times e to the kt, and then I'm going to write that as a e to the kt. And it's quite okay to redefine your arbitrary constant as long as you state what you've done. So a in this case is e to the c. And once you get good, you can jump straight from this line to this answer. This is quite a common answer, especially with population models. Okay, so that is the general solution, P equals AE to the KT, for this differential equation. Okay, and we've got the arbitrary constant A, and then the proportionality constant K. So, let's go back to the question. We're asked to find P in terms of T. We've still got 2 constants kicking around, so let's find values of those. And we're going to do that by considering, first of all, this piece of information. Initially, the population is at 12,000. That means mathematically, T is 0, P is 12,000. Okay, the word initially means T is 0, and we're told the population is 12,000, and P is a population. And then we're also going to use this piece of information as well. And this tells us that T equals 24, because it's 24 hours after the initial population, and we're told that's what T measures. And we know that P is 200,000 at this point. So it's 2 pieces of information that will allow us to find our two constants. So first of all, the initial population was 12,000. So that means 12,000 is going to equal AE to the 0. Doesn't matter what K is. If I'm plugging in T as 0, that KT is going to be 0. So that tells me that A, therefore, is 12,000. That gives me a value for A. So P is now 12,000 e to the kt. And then the other piece of information is going to give us our value for K. So when T is 24, P is 200,000. That gives us 200,000 equals 12,000 e to the 24k. And make k the subject. What I'm going to do is I'm going to divide by 12,000. I'm going to take the lateral log of both sides, and then I'm going to divide by 24. Okay, so I'm going to do all that in one step. So the 24th times the natural log of, I just cleared it. Start again. The 24th times the natural log of, it was 200,000 divided by 12,000. And that gives me K is 0.117225 and so on. I'm going to write my answer with 3 significant figures there. So therefore P is equal to 12,000 e to the 0.117 t. Okay, there we go, that's P in terms of t. Okay, that answers part A. Part B. According to the model, when does the population exceed 10 million? Give your answer to the nearest minute. Okay, so P is 10 million, which is 10 to the power 7. So this implies that T is going to be, again, I'm going to divide by 12,000, take the log of both sides, and then divide by K to make T the subject. That's the natural log of 10 million divided by 12,000. Okay, so that's making T the subject once I've plugged in K is, once I've plugged in P is 10 million. And I'm going to use the value of K which the calculator gave me, not the rounded value of K here. So on my calculator, I'm going to do 1 over K, which is my answer, times the natural log of, and it was 10 million divided by 12,000, which is the same as 10,000 over 12. So I get 57.37 and so on. Now once it to the nearest minute, so I'm going to say that that is 2 days. Okay, so subtract 48 hours from that. 9 hours. Okay, subtract 9 from that, and then times the remainder by 60, 22 minutes. That's my answer. Okay, 2 days, 9 hours, and 22 minutes. Finally, part C. I'm not going to write this, just going to verbalise it. Criticise this model. We can criticise this model because if we look at what P is, as T tends to infinity, P tends to infinity. In other words, there's no limit according to the model as to the size of the population. That's not realistic. So that's the kind of thing you need to be saying there. It's quite often a little 1 marker thrown in these types of questions. So you should make sure you have an answer ready for that. Okay, that's the first one. I'm going to do 2 more this video, and then I'm going to do a separate video for a really big 4th one. So, example number 2. Sand pours into a large box at a constant rate of 100 kilograms a second. Sand leaks from the bottom of the box at a rate of 12 m kilograms per second, where m is the mass of the sand in the box. Model the situation by a differential equation and solve the ODE given that the mass of sand in the box is 1 ton when t is 0. Okay, lots going on here. So we've got sand is poured into a large box at a constant rate of 100 kilograms a second. But also, it leaks from the bottom of the box at a rate of 0.5 m kilograms per second. So this is going to be an input. So dV by dt, dm by dt. And I know it's dm by dt because it's mass over time, and we can see the units here. Kilograms is mass and seconds is time. So it's dm by dt. That is going to be 100 Okay, so that's the sand pouring in. But you've also got dm by dt equals minus, equals minus a half m, which is sand out. And it's minus a half m because it is leaking from the box. So the rate of change of mass is decreasing. So these two combine, they're happening at the same time. So together we have the rate of change of mass of sand in the box is 100 minus a half m. Okay, so that is the model. Okay, the rate of change of mass is the 100 going in and the minus a half m leaving at the bottom. So this is now a differential equation, which we are to go ahead and solve, and then we can use the extra knowledge that's given to us to find a particular solution to this. So the only method that we know is separation of the variables. So that's exactly what we're going to do. So we're going to divide both sides by the 100 minus a half m. I'm going to times both sides by dt, don't forget that. That's a 1 on the right-hand side. Okay. So I've divided by this, so that's left me with a 1, and I've times by dt. And now I need to put my integration symbols in. There we go. And now it makes sense. This one here, I should make the top the differential of the bottom. That's one of my special cases. So to do that, I need the top to be minus a half, because that is the differential of the bottom, which means I need to essentially times it by minus 2 as well. There's a correction. Okay, so I've times the whole thing by 1, so it's the same integral, nothing's changed, but I've written it such that the top is now the differential of the bottom, so that I can just say this integral is the log of the bottom. And the integral of 1 with respect to t is t, and don't forget your arbitrary constant. Although I don't need that quite yet, because there is still an integral symbol there. Okay, so that's going to be minus 2 times the natural log of mod of the bottom. That's 100 minus a half m. And that's going to equal t plus c. And now I can raise, divide by the minus 2. And then raise both sides as a power of e. So I'm going to say 100 minus a half m equals ae to the minus 2t. Minus a half t. So divided by 2, and again, just like in my previous example, I redefined my arbitrary constant, so I should write how I've done it. So a, in this case, is e to the minus a half c. You don't have to redefine it, this does look quite a lot nicer. And in fact, I'm going to put a half there as well, just because I'm going to make m the subject, I'm going to end up timesing by 2, so that just means it's just a rather than 2a. Okay, so I can make m the subject of that. So m is going to equal, so I'm going to times it by 2, and then I'm going to bring that across the other side. So that's 200 minus ae to the minus a half t. Okay, so that's the general solution to the differential equation. This represents the family of curves which satisfies the original differential equation here. Now we need to find the particular solution, and to do that we are going to use the extra information given to us in the question. So we are told that the mass of the sand in the box is 1 ton when t is 0. So everything's in kilograms and seconds. Okay, so because it's in kilograms, I need to convert the ton to kilograms. So that is 1,000 is going to equal 200 minus a e to the 0. That tells us that a is minus 800. And then we can conclude that m equals 200 plus 800 e to the minus a half t. And that is the answer. That's the answer to the question. Now, occasionally you'll be asked to sketch the curve. So it's good to have an idea of what this curve looks like. You are allowed a graphical calculator, but not everyone will have one of those. Now, we know that when t is 0, m is 1,000. That was the condition. So it's going to cross up there at 1,000. And we also know that we can see that when t tends to infinity, this term is going to disappear. because it's e to the negative infinity. So that's going to go to 0. So we're left with 200. So we're going to get a horizontal asymptote at 200, and we're going to have an exponential decay as it comes down to that. So we're going to have this shape, and it is an exponential decay. It's just decaying to 200 rather than your traditional decaying to 0, and that's because of the 200 plus. And there we go. That's what the graph would look like if you were asked to sketch it. Okay, final example of this video, example number 3. Newton's law of cooling states that the rate of temperature change of an object is proportional to the difference in the temperature of the object and the surrounding area. Part A, form a differential equation. That's what ODE is, ordinary differential equation, to model Newton's law of cooling, where T degrees Celsius is the temperature of the object at time t minutes, and the ambient temperature is 20 degrees. And then solve this differential equation and sketch some solution curves which correspond to initial temperatures of 100, 50, 20, and 0. Okay, so first of all, form an ordinary differential equation. So let's break down what's going on here. So Newton's law of cooling states that the rate of temperature change, well, that is denoted as dt by dt. Okay, temperature is capital T, time is lowercase t, and the rate of change of the temperature is d capital T divided by d lowercase t. Excuse me. That is proportional, okay, times the difference in the temperature of the object and the surrounding area. So T is the temperature of the object, and the question says the surrounding area is 20. Okay. And there we go. That is the differential equation. So we should go ahead and solve it. So form a differential equation, and then part B, solve the differential equation. So I'm going to get T minus 20, all under the number 1, dt, is going to equal K dt. Again, popping our integration symbols so it makes sense. The top is the differential of the bottom, so that is going to be the natural log of the modulus of T minus 20 is equal to kt plus c, and that tells us that T is going to equal 20 plus a e to the kt. And yeah, that needs to be primary constant. So a equals e to the c. There we go. Okay, so that's the general solution. And it's Newton's law of cooling. So the temperature change is actually going to be decreasing. So K is actually a negative number. So I'm going to pop a negative there so that K is positive. So I'll just get a minus K. That follows all the way through. It's not incorrect if you don't put the negative there, because that differential equation did satisfy Newton's law of cooling. But if you want K to be positive, then it should do that. Otherwise, the temperature is going to blow up, and actually it's going to converge onto the ambient temperature. So it is a negative exponent. Okay, and then we also want to sketch solution curves to this for different initial temperatures. So when T equals 0 and capital T equals 100, that tells us that our arbitrary constant, A, is going to be 80. When T equals 0 and capital T is 50, that tells me that my arbitrary constant is going to be 30. Okay, 20 plus 30 e to the 0 is 50. Or when T equals 0 and capital T is 20, then that tells me that A is 0. And if T is 0 when capital T is 0, then that tells me that capital A is negative 20. So I end up with kind of these 4 arbitrary constants, these 4 particular cases, which satisfy the question. And we're asked to sketch these. So we need to go up as far as 100 on my capital T axis. there. And then I've got a lowercase t, and all of them are going to converge to 20, which makes sense because that's the ambient temperature, it's the temperature of the room. So you can imagine this is a cup of coffee maybe, and as time increases, the temperature of the coffee will converge to the temperature of the room. So if you're going to start at 100 degrees, then it will exponentially decrease to 20. Or maybe you're going to start at 50 degrees, in which case it will exponentially decrease to 20. Or if you start at 20 degrees, you're starting at the same temperature as the room, then A is 0 and you're left with T equals 20, which would just be that line, it would just be the asymptote, it would remain at 20 degrees for all time. Or if we're starting at 0, so it's not a cup of coffee anymore, maybe it's something you've just taken out of the freezer, then the temperature will increase. And again, it follows that exponential decay, but it's upside down as the temperature increases towards the ambient temperature of the room. Okay, so that's Newton's law of cooling. Okay, right, I'm going to do one more video, which is a really big application question, so check that one out, that'll come next.